Good morning, sir. My name is Nandini. I am from CSC B section. Today, my topic is theoretical barriers. Why maintaining entanglement is difficult. First, we are moving to the outline of the theoretical barriers, that is introduction, decoherence, environmental noise, measurement disturbance, quantum state fragility, limited quantum error correction, entanglement decay, disentanglement, scalability issues, and then conclusion. Theoretical barriers, why entanglement is difficult. Quantum entanglement is a cornerstone of quantum technologies like quantum computing, quantum communication, and quantum cryptography. However, maintaining entanglement over time and distance is extremely challenging due to several theoretical and practical barriers. Understanding these barriers is essential for advancing quantum application. And then introduction. Quantum entanglement is a phenomenon where two or more particles share a correlated quantum state, meaning a change in one particle instantly affects the other even if separated by large distances. Entanglement forms the foundation of quantum computing, quantum communication, and cryptography, enabling faster computation and ultra-secure data transfer. However, maintaining entanglement is extremely challenging due to its sensitivity to environmental disturbances, measurement effects, and natural instability of quantum states. Generally, quantum entanglement is one of the most fascinating aspects of quantum mechanics. It is the basis of many advanced technologies like quantum computers and quantum modules. But while it's easy to create entanglement in labs, and small disturbances, noise, or even the act of observation can destroy it. In this presentation, we will discuss the main theoretical reasons why maintaining is so difficult and why it remains one of the biggest challenges in modern physics. Yes, first we are moving to the decoherence. Decoherence is the process by which a quantum system loses its quantum behavior due to interaction with the surrounding environment. When the entanglement particle interacts with the air molecules, heat, light, or vibrations, its quantum state becomes mixed with the environment, causing the system to behave classically. The first and most significant barrier to maintaining entanglement is decoherence. In simple terms, decoherence happens when a quantum system interacts with its surroundings, like air molecules, heat, or even stray electromagnetic fields also. These tiny interactions disturb the quantum state and causing it to lose its coherence, behave like a normal classical particle. Once decoherence occurs, the entangled link between particles is broken. This is one of the biggest reasons why quantum computer must operate at extremely low temperature and in highly isolated environments. Next we are moving to the environmental noise. Environmental noise refers to random external disturbances that affect a quantum system and disrupt entanglement. Even when system is carefully isolated, small influence such as temperature fluctuations, magnetic fields, vibrations, or background radiation can alter the quantum state. And these tiny disturbances introduce unpredictable changes in the phase of energy of particles, causing errors and loss of coherence. Environmental noise is therefore a major limitation in sustaining stable entanglement over durations. In the quantum world, the second theoretical barrier is environmental noise. Even the smallest disturbance matters, slight temperature shifts, stay magnetic fields, or mechanical vibrations can disrupt the fragile entangled state. Unlike decoherence, which is a general loss of quantum behavior, environmental noise specifically comes from external physical sources that interact with the system. That's why quantum computers are built inside vacuum chambers cooled near absolute zero and heavily shielded to minimize the environmental influences. Despite all these precautions, complete elimination of noise is impossible, which makes it a persistent challenge in maintaining entanglement. Next, we are moving to the measurement disturbance. In quantum mechanics, measurement itself disturbs the systems. According to the Heisenberg uncertainty principle, it is impossible to observe or measure a quantum state without altering it. According to the Heisenberg uncertainty principle, this fundamental principle limits our ability to monitor or verify entanglement without disrupting it. The third theoretical barrier is measurement disturbance. In classical physics, we can measure a system without changing it. For example, measuring the temperature of water doesn't alter its state much, but in quantum mechanics, observation itself affects the system. When we measure one particle in an entangled pair, the measurement collapses its wave function and destroys the dedicated correlation with the other particle. This means that even trying to check or confirm entanglement can end up breaking it, which is a fundamental limitation of quantum mechanics, not just a technical problem. And then next we are moving to the quantum state fragility. Quantum state fragility refers to how delicate entangled states are. Entangled particles exist in precise superpositions, meaning their states are carefully balanced. And then even tiny disturbances in phase, amplitude or energy can disrupt these correlations, causing the entanglement to break. This extreme sensitivity makes it difficult to maintain entanglement over time or across multiple particles. Environmental interference, interaction with external particles, electromagnetic fields, interaction with external particles. The fourth theoretical barrier is quantum state fragility. Entangled states are extremely delicate. They exist in a precise superposition of possibilities. Any slight perturbation like a small phase shift or tiny energy change can destroy the correlation between particles. You can think of it like a tightrope walker. Even a small wobble can cause them to fall. This fragility is one of the reasons why quantum computers require very controlled environments and extremely precise operations to preserve entanglement. Next, we are moving to the limited quantum error connection. Quantum error connection is a technique used to protect quantum information from errors and decoherence. Next, however, current error correction methods require many physical qubits to protect a single logical bit. This makes it resource intensive and difficult to scale, limiting the ability to maintain entanglement over long periods or across large quantum systems. Despite being theoretically possible, practical implementation of quantum error correction remains a major barrier. The fifth theoretical barrier is limited quantum error correction. In classical computers, error correction is straightforward. One extra bit can detect and correct mistakes. In quantum systems, it's far more complex. To protect just one logical qubit, we often need dozens of physical qubits. This makes maintaining entanglement across multiple qubits extremely challenging. So while quantum error correction can help, it is still limited by current technology, and large-scale preservation of entanglement remains difficult. Next, we are moving to the entanglement decay. Entanglement decay, also known as disentanglement, occurs when quantum correlations between the particles. Entanglement decay, also known as disentanglement, occurs when quantum correlations between particles gradually degrade or over time. Even without external measurement or disturbance, entangled states are not perfectly stable. The natural loss of coherence is called entanglement sudden death and can happen unexpectedly. Entanglement decay limits the time span over which quantum system can reliably maintain correlations. Next, we are moving to the scalability issues. Scalability issues means the seventh barrier is scalability issues in theoretical barriers. Entangling a few particles is manageable in a lab, but as we increase the number of qubits, maintaining perfect correlations becomes extremely difficult. Each new qubit adds complexity, more interactions, or more potential sources of error. This exponential in difficulty makes large-scale quantum computers and networks a major technical and theoretical challenge. Overcoming scalability barriers is crucial for realizing practical quantum technologies. Net finally conclusion. Maintaining quantum entanglement is extremely challenging due to several theoretical barriers including decoherence, measurement, disturbance, quantum state fragility, limited quantum error correction, entanglement decay, scalability issues. Understanding these barriers is essential for advancing quantum computers, quantum communication and cryptography. Thank you, sir.